Okay, we're continuing our discussion of capacitors and capacitance, and I want to think about what a capacitor is. It's, remember, two plates separated by a certain distance, and a bigger capacitor can store a larger amount of charge. It's a way to store charge, and the more charge you store, the more energy you store. So that's one way to think about what a capacitor is. And one of the things we're going to kind of make sense, perhaps, is that if you have more plates, more area of the plates, then you're going to be able to put more charge on there because the charge spreads out. And you can only be able to put so much charge on a given plate. But the bigger the plate, the more room there is for the charge to spread out, therefore the more charge you can put on a given plate, all other conditions being the same. Similarly, as you bring these two plates closer and closer together, one being positive, one being negative, then the amount of charge you can put on both plates is also going to increase, because as you get closer to the opposite charged plate, you're going to be able to attract more of the, say, positive charge on the positive plate, knowing there's a negative charge here on the negative plate. You're going to have more ability to put more positive and negative charges on the plate from an external source like a battery. So those are two things to consider conceptually as we talk about capacitors. And here's the way we can actually calculate the value of the capacitance. We've talked about the voltage between two plates where the electric field is uniform. You can multiply the electric field strength times the distance between the plates to get the voltage. That was the example we did in the last video. And the strength of the electric field is given by, between the two plates anyway, is given by the charge density divided by the permittivity of free space. We've been talking about that equation, sigma divided by epsilon 0. That is our electric field, so we can substitute that in for E, multiply that times the separation between the plates, and that's going to give us the potential difference between the two plates. All right, so another way to think about sigma, by the way, is that sigma is equal to, that's the charge density, remember, sigma. It's equal to the charge on the plate divided by the area of the plate. Okay, so I'm going to substitute this in here. I'm going to say that, okay, this is also equal to the charge on the plate divided by the area of the plate, that ratio times D divided by epsilon 0, which I can also rewrite as Q over A epsilon 0 times D. All right? Or if you like, I can rewrite it as QD over A epsilon 0. That is equal to the potential. Now I'm going to go to my definition of capacitance that I talked about in the end of the last video. And see if I have room over here. I do. Okay. I remember Q is equal to CV. That's the Chula Vista equation. So my capacitance is equal to charge divided by V. So I'm going to substitute in here. This is my V right here. That's my voltage. Okay. So what I'm going to do is I'm going to say this capacitance is equal to Q divided by Q times D over A epsilon 0. Notice that the Q's cancel. This is going to give me an equation for capacitance that I hope you can see on the video. Can't tell? I think you can. It's equal to, I'll write it out over here, Q over QD over A epsilon 0. The Q's cancel, and it's going to become equal to A epsilon 0 over D. This is my equation for capacitance, for two parallel plate capacitors, right there. I have to move my camera just a tiny bit. So this is my equation. All right, and if you look at how the units work themselves out, let's see if we can get this to work out to something we can work with. This is going to be farads. That's the unit of capacitor. As you've seen in lab, we've talked about it. That's a unit of farads. And so the area is in units of meters squared. The D is in units of meters. then epsilon 0 is equal to, let's see, Coulomb squared over Newton meter squared. Okay, so these cancel. So a farad, 1 farad, is equal to a Coulomb squared per Newton meter, which is not a particularly interesting or insightful unit, but we can work with that. Okay, so that's what a farad is, but that's what's going to be the unit of capacitance. So what that means is for any two plates that we're putting near each other, if we know the area of the two plates, and the areas are going to be identical for capacitors, for any capacitor that we're going to work with, and you just take the area of one of the plates, that's your A. The D is the separation between the plates, that's going to be in meters. So if you're only separated by 1/10 of a millimeter, remember that's 10 to the minus 4 meters, then epsilon 0 is the 8.85 times 10 to the minus 12. It's going to be a really small number. So let's see what size capacitors we can possibly build, which is what you're going to be doing in lab. And there it is in the PowerPoint slide. You can see it. You might have to open up the PowerPoint to take a look at it, but what I wrote on the board is on this slide. And of course, this is a way you can also store energy, which I'm not going to get into so much at the moment, but when you store a charge, you're also storing energy, and the next slide in the PowerPoint shows that. So I'm going to do a calculation. This is not in the PowerPoint, but I'm going to do a calculation for how big a capacitance you can build, kind of like what you're going to do in lab. So let's just say we have a couple sheets of aluminum foil. There's one, it's 10 centimeters by 10 centimeters, let's just say. And we get another one on top of it, like this, is also 10 centimeters by 10 centimeters. That means the area of this sheet is going to be equal to 10 centimeters squared, or 100 square centimeters, which we've already found in the previous slide. That was going to be equal to, as you multiply each centimeter by 1 meter is 100 centimeters, 1 meter is 100 centimeters. So you get how many square meters 100 centimeters squared is equal to, or 100 square centimeters are equal to. And if you do the work here, you'll get that this is equal to 0.01 square meters. So that's my A. Now, let's see, how close can we get two sheets of aluminum foil to each other? A millimeter is pretty close, but I bet you we can do better than that. In lab, we're going to try to get them as close together as possible, and you'll actually see it. But let's just say that we get our separation between these two sheets. I'll say, okay, that's the separation, the D, between two sheets. Well, if we put another sheet of paper in there, we could get it conceivably as narrow as maybe a sheet of paper. And that's less than 1/10 of a centimeter. I'm just going to say that that's equal to about 1/100th of a centimeter. I'm sorry, 1/100th of a millimeter. It's less than 1/10 of a millimeter. It's going to be pretty narrow. And we could try to figure out what it is, but I'm just going to go with that for now. I'm sorry, millimeter. So 0.01 millimeter is going to be equal to 10 to the minus 5th meters. Because I know that 1/10 of a millimeter is 10 to the minus 4, and I know that 1 millimeter is 10 to the minus 3 meters. So 1/100th of a millimeter is 10 to the minus 5th meters. Let's calculate what the capacitance is that we can expect from this. I'll use the same equation I've been using. Capacitance is equal to epsilon 0 times A divided by D. Well, I know all these. I know epsilon 0 is 8.85 times 10 to the minus 12. A is 0.01 square meters. D is 10 to the minus 5th meters. Okay, let's do the math and see what we get here. If I multiply all these out, I'm going to erase this stuff below. If I multiply all of these out and divide, I'm going to get, let's see, this of course is units of Coulomb squared per Newton meter squared. So if I multiply this out, I'm going to get farads. It's going to be 8.85, I know that. That's going to make it 10 to the minus 14th, and then divide it by negative 5, I'm going to get 10 to the minus 9th. So what this means is this is equal to, looks like a really small number, doesn't it? Really small capacitance. It's 8.85. And the units for when you have 10 to the minus 9th, 10 to the minus 6th is micro, and 10 to the minus 9th is nanofarads. That's really small value of capacitance. So to get bigger values, there's things we can do, and we'll talk about that. But for practical capacitors, it's hard to get them really big, as you can see, because you're only going to be able to get those two plates so close together. And you're only going to get so big an area of plates that you can stick into something really small like the capacitors we're using in lab. So we'll talk about ways to get this value bigger. That's a really small value of capacitance. That's how you calculate it for a parallel plate capacitor. Okay, I'm going to end this video, and we'll keep talking about capacitors in the next video.